In this video, we're going to discuss an example related to complete metric spaces, and this example is in fact an exercise under section 1.6 of the book Introductory Functional Analysis with Applications. Okay, uh, what we are given is we're given a complete metric space. Okay, a complete metric space M row, and we're given another function. Let's see. We're given a function m cross m to r such that for all xy belonging to m, we have row xy to be equal to row xy over 1 plus row xy. This is what we are given, and we're writing this in a much compact notation as something like this. Okay, we're given two things, a complete metric space and some another metric. Then we're supposed to prove that this new metric space, okay, now we're going to prove that this is indeed a metric in a separate video. I'm not going to do it in this video. I'm just going to use the fact that row cap, okay, row hat or row cap is indeed a metric. Okay, this is a metric, this is a metric, this is a metric. We're going to prove that this is a metric in a separate video. Okay, that's all. And we need to show that this is a complete metric space. Now to do that, like we do in any analysis question, we're going to suppose that the given conditions hold. Okay, conditions hold. Now in order to prove that this is a complete metric space, we need to show that every Cauchy sequence in the given metric space is convergent. Okay, let xn be any Cauchy sequence in the metric space, sequence in M row dash. Now we're choosing any Cauchy sequence. So if we can show that any Cauchy sequence is convergent, it means that no matter what Cauchy sequence we choose, it will always be convergent. So every Cauchy sequence will be convergent in the end, which makes the metric space M row complete. Okay, now we're going to do it's a little bit of a tricky problem. So instead of choosing epsilon all the way, epsilon in the beginning, let's choose two things. Okay, so because of the nature of this metric, we would want to use a different approach. All right, let's see. Let the given condition. Okay, since, okay, not since, let me just simply take two positive numbers. Let epsilon naught be a positive number and epsilon 1 be a positive number, be arbitrary positive numbers, arbitrary, and such that epsilon naught is less than 1 over 3. You can take any number less than 1 for this purpose. Okay, you can take any number less than 1 for this purpose, and I guess the book provides a hint to this problem, and I guess the book takes 1 by 2. I'm going to take 1 by 3. Alright, you can take 1 by 4, 1 by 5, 1 by 9, 1 by 10, whatever, 1 over 1, 2 over 3, or whatever you want to take, but make sure that it's less than 1, otherwise we'll be in trouble. Alright, and uh, epsilon 1 to be, since we're taking one of them to be less than 1 by 3, we're going to take the other one to be greater or equal to 1 by 3, obviously. Since xn is a Cauchy sequence, by definition of a Cauchy sequence, what are we going to get? Cauchy sequence, not Cauchy definition. Cauchy sequence. Since xn is a Cauchy sequence, there exists some m, a positive number m, belonging to Z plus, such that whenever we take n m2 indices to be greater or equal to m, we get something like this, epsilon naught. But I'll have to make some more calculations, so I'm just gonna write epsilon naught like this. Okay, epsilon naught like this. Now let's see. Now we've taken epsilon naught to be less than 1 over 3, right? So we're going to make some calculations now. xm less than epsilon naught means it's less than 1 by 3 already. So if we subtract 1, first of all let me write it like this, and so that if we subtract 1 from here, we're going to get minus 2 over 3. So 1 minus, okay, 1 minus rho xn xm is greater than 2 over 3. Alright, and this obviously means that it's positive, so we can take the reciprocal and obtain to be less than 3 over 2. Okay, this is what we are going to get due to non-negativity. Also, now we want this inequality. We are choosing some number less than 1 initially to make sure that we get this to be positive. Okay, in order to get this to be positive. So for example, if we take something like 2, then we're going to get, if we subtract 1, we're going to get something like this, minus 1 to be less than what do you call it, let's say 3, then less than 2, so 1 like this. What are we going to get? Let's say minus 3 means, okay, it's 2, so minus 2, so it's going to create a little bit of trouble. That's why I'm choosing some number less than 1. Any number less than 1 will do. Okay, this is it. Let's wait for a second now. Uh, what did we have initially? Let's see. We have it, right? This thing. Rho dash equals rho over 1 plus rho. Since the numerator is less than the denominator, it's obviously less than 1. So 1 minus rho dash is greater than 0, which makes sense right here, which is quite redundant. But if we solve it for rho, we're going to get something like this. And on simplification, we'll get something like this. Now this is the reason why. This is the reason why I'm doing all of this. Okay, I'm doing all of this. Now, let's see. Let's see. We've obtained this. Let's call it equation 1. Now, what about, okay, 3 over 2, right? So, rho xn xm. Rho xn xm was less than epsilon naught. Okay, was less than epsilon naught. Like this. Initially, I've taken it to be less than epsilon naught. Okay, less than epsilon naught. Now, since this is positive, I'm going to divide both sides of this inequality by this, whatever this is, without altering the inequality sign. Fair enough. Now, since we know that now this holds for m and n to be greater or equal to m, we get under these assumptions. Okay, we're getting it under these assumptions. Okay, that's why I'm writing it once again so that you don't get confused. Next, this was less than, this was equal to, this was less than, okay, this epsilon naught remains as it is, and using 1 we're going to get this to be less than 3 by 2, which means I'm going to replace this thing right here with 3 by 2 using 1. And this thing right here, this is simply rho xm xn. Alright, so what are we going to get? That is, for mn to be greater or equal to m, we get this part is rho xn, sorry, we don't have this arrowhead or cap or hat, whatever that's called, I'm totally unaware at the moment, to be less than 3 by 2 epsilon naught. It's perfectly okay to work with this 3 by 2, but I prefer getting epsilon or epsilon naught in the end. So if only I had 2 over 3 epsilon naught instead of just epsilon naught, I would have ended up with epsilon naught. So I should have taken 2 by 3 epsilon naught initially, okay, so that these calculations still hold. 2 by 3 epsilon naught is less than epsilon naught. These still hold. Okay, since this is a positive number. Now, I'm using definition up to this point, and this is just a redundant part. I'm not proving or taking less than epsilon naught for the calculation. I'm taking 2 by 3 epsilon naught. The the application of the definition ends right here, and this is just a redundant part of the inequality. Okay. Now, so 2 by 3, these calculations remain the same because ultimately we're going to get less than 1 over 3, and I'm going to take 2 by 3 epsilon naught, 2 by 3 epsilon naught, so 2 by 3, which is equal to epsilon naught. So what did we show? We've just shown that for epsilon naught greater than 0, for any epsilon naught, for any epsilon naught belonging to 0, 1 by 3 positive but less than 1 by 3, there exists some positive integer m such that whenever we take n and m, or m and n, to be greater or equal to m, we get rho xn xm to be less than epsilon naught. Okay, this is what we have just proven, and this is kind of a proof of the fact that we're taking x. We initially have taken this to be Cauchy sequence in m rho hat, and this inequality kind of like it's a part of the proof for the fact that is Cauchy sequence in the original space m rho. Okay, this is something like this, but the proof is obviously not complete because I'm taking only those positive numbers which were uh, less than 1 over 3. Now, for any epsilon naught greater or equal to 1 by 3, we can choose any m which corresponds to one of the epsilon naught less than 1 by 3, obviously where epsilon naught is greater than 0, and obtain that, and one of the choose corresponds to any one of the epsilon naught, and see that whenever what do you call nm is greater or equal to n, we get rho xn xm. Since it was initially for epsilon naught, we're going to get something like this, but since epsilon 1 is by our choice greater than epsilon 1, less than epsilon 1, we're going to get something like this. So for any epsilon 1 to be greater or equal to 1 by 3, this inequality still holds. Okay, so for let's consider this number line, that's 0. So up to this point, for values within this interval, we're going to choose m for probably for separate. We're going to choose m for each value, and for this part of the positive line, any one of these m, it'll work. Okay, that's we've just shown. So what can we say? For these, we can choose an m. For these, one of these m will work. So basically we can choose an m for these as well in order to get this inequality. So let's say let epsilon greater than 0, then as per our discussions, as per our discussions, there exists m belonging to z plus such that nm nm greater or equal to m gives rho xn xm to be less than epsilon. Why? Because of something like this. Let me repeat it a little bit. Okay, we're taking epsilon over here. Here we have 1 over 3. This is 0. Now since epsilon is positive, it can be within this interval or within this interval. Okay. Now if epsilon is in this interval, epsilon is here, then epsilon takes one of the epsilon naught values, and for these we can get, for every one of these we can get some m belonging to z plus. And if epsilon is greater or equal to 1 by 3, obviously one of these m would work. Okay, that's why we can say that if we take any positive epsilon, then we can find the positive integer m such that n and m, two indices, to be greater or equal to m gives this condition, this inequality, which means so xn 1 to infinity is a Cauchy sequence, in m rho. Okay, so initially we've taken this to be a Cauchy sequence in m rho hat. Okay, this was a Cauchy sequence in m rho hat, but we have shown that this is a Cauchy sequence in m rho. So in order to prove, first step that we have used is that take xn to be a Cauchy sequence in m rho hat, and in the second step, what did we do? Prove that xn is a Cauchy sequence in M row. Okay, that's what we have done. Now let us go back to the given conditions. What did we have? We had that M row is a complete metric space. M row is a complete metric space. Take any Cauchy, this is any Cauchy sequence, okay? Any Cauchy sequence. Now due to completeness, since M row is a complete metric space, M row is a complete metric space, complete metric space, it follows that Xn is convergent, because in a complete metric space every or any given Cauchy sequence is convergent. Okay, is convergent. Let the sequence Xn converge to X. Okay, we now claim that step 3, what did we do in step 3? Xn converges to X as M row is complete. We are using the given condition here. Now in the end, what are we going to show? Xn converges to X as X in the metric space M row, whatever that is, hat, tilde, whatever you want to call it. I'm totally blank. I don't remember the names of such notations. I'm really sorry. Now we claim that now this was in M row. All right. We now claim that limit n tends to infinity, Xn is equal to X in M row dash. Now to prove the convergence, let us again suppose epsilon greater than 0 to be arbitrary. Okay, let us again suppose this to be arbitrary. Then there exists some n belonging to Z plus such that n greater or equal to n gives, what does it give? Since this is convergent, we're going to get something like this. Okay, we're going to get something like this, but I do not need row here. I do not need row here. Rather, I need row tilde or row hat or row cap or whatever that is called. Okay, so I'm going to divide both sides of it by 1 plus row xn comma x. Now this is totally valid because 1 is greater than 0, row is greater or equal to 0, so 1 plus row is greater than 0. Okay, now one more thing. Now we can write this as obviously for n greater or equal to n, this is equal to, let me drag it down a little bit. Okay, is less than epsilon over 1 plus row xn x. Okay, now let us consider this thing. let us consider this thing. This is obviously, okay, let's see, 1 plus rho is greater or equal to 1 plus 0. So 1 plus rho is greater or equal to 1, which means 1 over 1 plus rho is less or equal to 1. So this thing right here is less or equal to 1. So this is equal to this is less or equal to epsilon times 1 over this whole thing is less or equal to 1. So we're going to replace it by 1. Since this inequality is more dominant than this inequality, we're going to get x and x to be less than epsilon. So we've taken any epsilon, found an n such that for n greater or equal to n, this thing holds. So thus, what did we obtain? For all epsilon greater than 0, there exists n belonging to z plus such that n greater or equal to n implies rho hat x and x is less than epsilon. That is, limit n tends to infinity, xn is equal to x in the metric space m rho hat. Okay, so but initially was any arbitrary Cauchy sequence in m rho tilde, and from here we have shown, and we have just shown that xn converges to x in the metric space m rho. Thus, since this was any Cauchy sequence, we can say every Cauchy sequence in m rho tilde or hat is convergent, that is, m rho is a complete metric space, Okay, all right, that's it for today. Thank you very much.